Before I get started here, I wanted to settle this issue with some homework without names on it. Is Caitlin Vera here? She hasn't got any credit for her homework. There was no name on it, but we have no credit for it, so that's serious. What about Sharon Wong? Also, no show. Just a reminder then, we got a quiz.
Thank you.
We got a quiz on this Friday, so everyone's aware of that. What we need to do next year is we've got a couple of really great representations for binary DLE data that we've gone through and spent some attention on, namely the Margulis and the Van Laar expressions, but we need to recognize that there are some limitations to them. One of the serious ones is that they treat activity coefficients as though they are functions only of composition, and ignore the fact that these can also depend on temperature and pressure. Now, the pressure issue is not so serious because except for very high pressure systems, the pressure dependence of activity coefficients is negligible. But that isn't going to be the case fairly often for temperature. So we've got two types of VLE data sets. We have the isothermal data sets, so for those it's not an issue because the temperature is constant across the composition range. But for the more common type of VLE data sets, namely those at constant pressure, it is an issue. And if that temperature variation between the maximum and minimum temperature achievable is greater than about 15 or 20 degrees, we may have a fairly serious issue with the temperature dependence of activity coefficients. So that's the issue. And another sort of secondary issue is that when we extend the Van Laar and Margulis expressions to 3 or more components, we don't do quite as well as we wish we would. It's still pretty good, but it would be nice if we could do better. And it turns out that both of these issues are addressed by another formulation, another 2-parameter formulation, different from Van Laar or Margulis, that we know of as the Wilson equations. Let's see if this is going to allow me to write. Let's see here. Let's see. The present button doesn't seem to be here. Yeah, maybe it's going to work now. And these are the Wilson equations. And they're quite old now, but they still are considered to be the best 2-parameter representations of VLE data. The excess Gibbs energy in the Wilson formulation is given by the following expression, and you can see the constants that are involved in these capital lambdas. They're in fact not constants actually, they're functions of temperature, and we'll see that in just a moment. But when I extract the activity coefficients out of this general expression for the excess Gibbs energy by the formula that I've got here, this is the result. So these are the expressions that replace our Margulis or Van Laar expressions. And you can see they involve these capital lambdas 1, 2, and 2, 1. And mathematically, they're a little bit worse than Van Laar Margulis. They don't allow us to do a least squares linear regression to evaluate those parameters. We have to resort to nonlinear least squares if we're going to try to fit those parameters from a given VLE data set. Let's take some look at these gammas, these lambdas. And it's important that we understand how they are formulated. V2 and V1 are the molar pure component liquid molar volumes. And they show up here and as a ratio, and they're, let's see if I can write it, they're tabulated at 25 degrees C. And those are the values that are used for it. And the fact is, since they have approximately the same type of temperature dependence, and it's fairly weak to begin with, the ratio of V2 to V1 is considered temperature independent. And we can just plug in those values that we get at the 25 degrees C. And then we have exponential of these little parameters A12, and A21. Those are constants, and in fact, those are the real Wilson parameters. And they can be evaluated, regressed from a given VLE data set, and that has been done for many, many systems. Now, an interesting quirk is that these are given in the units of calories per mole. And that means that the R value that we use in the Wilson equations is the one that involves calories, and that's at 1.987 calories per mole degree K. Just a little quirk. Well, nothing much more to be said about this, except you can see straightforwardly if we can evaluate, if we have A1 and A12 and A21, we can evaluate the lambdas for the system of interest, plug it into these equations, and proceed as before. We're calculating vapor-liquid equilibrium, things like dew points and bubble points and compositions of phases of unknown composition and the like. Pretty much everything we have done before. Everyone clear on that? Because you're going to have a homework problem with the Wilson equations here in the next set. Now, for a component in a ternary or higher solution, it gets messier. These activity coefficients look like this. And just to give you an idea of even just going to the ternary of how complex that can look, if it allows me to do it. Unbelievable. That's what it looks like. So again, straightforward, but a little bit messy. Now, it's claimed that the Wilson equations, in cases where we have somewhat complicated vapor-liquid equilibrium behavior, that the Wilson equations will do better than Van Laer or Margulis. And here's an example of that. A system you wouldn't think would be too complicated, but ethanol and isooctane do form a rather complicated system. And you can see the way the data are here. These are the data points. As I've shown through here, it's not letting me draw. It's giving me problems today. But I think you can see then that the Van Laer best representation it can do is the dashed line. Not quite as good as what Wilson can do, which appears to be going right through the data points for this particular system. As for its ability to extend to 3 and higher components, another data set is kind of interesting to look at. This is for the acetone, methanol, acetone, methyl acetate, methanol, and acetone, methanol chloroform systems. The Wilson equation representation, this is for the experimentally calculated Y for the acetone. As given by the Wilson equation, you can see beautiful straight line against the experimental versus the calculated, whereas the Van Laer representation is not quite as good. So it's a representation of that fact as well. So what have we got now? We've got Margulis, Van Laer, and now we've got Wilson. But that isn't all there is to the story, but it's all that we're going to discuss in any detail, but I need to show you what other things are out there. And I really wish this animation would work, but it isn't. But let's take a look at other correlation methods, that is, in addition to the two that I've mentioned. One that you'll see in the literature here is the non-random two-liquid model, and that is 3 adjustable parameters. And another one is UNIQUAC, stands for Universal Quasi-Chemical. That's, again, got 2 adjustable parameters, and these are different architectures. And the reason I tell you about them is that you find them, these are native to Aspen, and so you'll find them as alternative representations for this behavior, although in this class we're not going to explicitly deal with them. Now, in addition to that, there are a number, I should at least tell you about this, there are a number of predictive methods. There are some rudimentary theories of solution that are very, very important, but they're pretty limited in their application. Regular solution theory is a very important one that deals with situations where we can identify all of the non-ideality with enthalpic effects and with molecules that are not too off from being spherical and similar in their chemical structure. And for the limited range of materials for which it is valid, it is actually predictive. We can, in other words, predict solution behavior from pure component behavior alone. The Flory-Huggins theory was developed to describe polymer solutions, where now we're looking at particularly either randomness or non-randomness of mixing that results from very different sizes and shapes of molecules that form the solution. Again, unfortunately, we don't have time to deal with that as well. And there are a couple other really interesting ones here. One is called the UNIFAC. That's been around since the 70s. And the idea of UNIFAC is that it will build up the description of molecular behavior by the behavior of the functional groups that make up the molecules. And if you can imagine that I can identify about 50 or so functional groups, and then look at the thermodynamic properties associated with those groups, I should be able to predict molecular properties by putting those together. And as far as the ability to predict individual molecular properties, that is really good. And that's been around for a very long time. But what's new about UNIFAC is that now it predicts functional group interactions, energetic and entropic interactions. And so what you need is a database for that is regressed backwards from published VLE data. But a quite large database was published before people realized how valuable this was. And so a trimmed down version of UNIFAC is available on Aspen. And to a certain extent, to the extent that you have this group database, it's predictive. That is, you can predict thermodynamic properties directly. Well, it got so good that then the database, as it built up further and further, got to be held privately in what is called the Dortmund database. Dortmund is a city in Germany, and that's where this is all done, and companies have to pay large amounts of money to get access to that database to use it. So it's kind of interesting, and that's a thing that is going on. But one that really kind of excites me is what's called COSMO. That's an acronym that stands for Conductor-Like Screening Model. And what it does, let me just tell you basically what it does and where we are with it, and why I'm kind of excited about it. It uses density functional theory to describe individual molecules. Now, the sizes and shapes of molecules are long known. We refer to them as van der Waals dimensions. Those have been known for a long time, and you don't need density functional theory for that. But what density functional theory will give you is a picture of the molecules. Here's a couple of examples that I show you here. They look a little bit like colored potato sacks, but these represent molecules, the surface of which is a map of charge density, positive or negative charge density. It has different extents. So the colors just represent, I think red is positive, blue is negative, green is neutral. So each molecule will have this pattern of charge density around its surface. Okay, then the next thing is to develop an architecture for describing how molecules for which we have the DFT characterization, how they interact with one another in multi-component solutions. And that architecture is in a state of evolution. The first stab at it about 20 years ago was pretty unconvincing. But that is being refined year by year. It is getting to the point now for a large number of systems that can actually give you ab initio predictions of thermodynamic behavior of multi-component systems. And I am convinced as we keep refining this model, it gets a little more and more complicated mathematically, but as we refine it, we're going to get to the point where we can actually predict BLE data. So that's the prospects in the future. Unfortunately, in this course, we don't have time to go into all of this, but that is something that would, in a more advanced course, would be, I think, an important subject. Well, let's go back to our world, and that is where we have VLE databases. And the biggest of all of these is the so-called CHEME base. You can find it in the library in the reference section. It's about 20 volumes with thousands of binary VLE systems characterized. And here's one page out of it that I want to spend a little bit of time describing. CHEME is it's just an acronym. It stands for Deutsche Gesellschaft für chemisches Apparaturwesen. There's an organization that was formed in the 1920s, and it's now an NGO. It continues to exist, and they keep adding to this database and collecting it. So let's look at all what is in one of these pages. It's really quite remarkable. First of all, this is for the system of acetone and hexane. It happens to be a constant temperature system that is being described. I think it's 20 degrees C here. It'll let me write. So one of the things we need to know, of course, are the Antoine constants for those components. And it gives you them here and two different ranges of the temperature for which it is valid. And it gives you the constants A, B, and C. But we need to know what the format is for Antoine's equation. This is it. I typed it in. That would be given at the beginning of the volume so that you would know it isn't repeated every time. So now we have that information. But now let's take a look. Here are the experimental data, and that's from what we build everything else from. And what that is, they have regressed those data to give you the Margulis constants. Here's A12 and A21, the Van Laar constants, the A12 prime and A21 prime. And it also gives you the NRTL and the Uniquac constants, but we're not going to be dealing with those. It gives you a plot of the YX performance here. And you notice that here we got a prominent azeotrope near the midpoint of the composition range here. It'll give you what the calculated limiting activity coefficients are for the two components based on the Wilson formulation. Because you remember, those limiting values of the activity coefficients are obtained only by extrapolation. And so if you're going to get those, you have to say, well, how did you do the extrapolation? It was based on Wilson. Here we see how well Margulis, Van Laar, Wilson, NRTL, and Uniquac did in predicting the data. And you can see they all did about the same. All pretty good. So this pretty much contains all the information you might want to know about this particular system. And as I said, there are thousands of such pages in the CHEME collection. So we should be aware of that. It's a little bit disjointed here, but I want to move on to another topic now, which I'm going to refer to as K factors. So this is what I've talked about here, and now I want to discuss what's referred to as the K-factor method for VLE calculations. Before I get started with that, this is not in your book, but it is another way of algebraically expressing vapor-liquid equilibria, which is going to be convenient for what we do then next, but you should be aware of it anyway. But it also identifies another type of system which is of interest to us, at least in some applications. We've made the statement long ago that we're going to assume that the modified Raoult's law is going to be good enough to describe anything that we might be interested in. But it turns out there's another interesting class of systems that can be described by simple approximation that we should also take a look at. And they are well described by what I call here the K-factor method. So let's get into it. We have a general vapor-liquid equilibrium equation here, as always, equating the fugacities of each component between the vapor and the liquid, and if we write it out with complete generality, it looks quite complex. But we can write this equation in the following format. We can say yi is equal to ki times xi, there should be an I there. And that means that ki is the ratio of all of this stuff. Now, there are two general types of approximations, one of which we're already familiar with, and that's what we've been using, and that is the modified Raoult's law. We're assuming that we're dealing with moderate pressure systems in principle here, so that we can make a lot of approximations that allow these phi terms to cancel out, and then the pointing factor is also generally small if the pressure isn't large. So that brings us back to the modified Raoult's law, in which these K factors are just equal to gamma I PIS over P. But strongly dependent on composition because the activity coefficients depend on composition. But there's another type of system that is particularly of interest in the petroleum industry, which was a big part of chemical engineering in earlier years. And that's a situation where we're dealing with molecules that are quite chemically similar, and these would be mixtures of the light hydrocarbons. And these are situations in which the Lewis and Randall rule is pretty good for both phases. And if I write that situation, I remember what the Lewis and Randall rule is. It ties up all of the non-ideality, if it exists, into non-ideality of the pure components. Yeah.
For number two there, the approximation, is that the approximation when gamma is just equal to 1?
We're assuming gamma is equal to 1 in this second formulation.
It's just
right.
an approximation. Type of
Yeah, and the reason for that is that this is then going to be limited to mixtures of molecules that are very, very similar. And mixtures of light hydrocarbons conform to that. So if we're dealing with mixtures of methane, propane, butane, stuff like that, those are all chemically so similar that they actually will conform to the Lewis and Randolph rule.
Is there an analogy here? It's the modified Raoult's law. We use that in situations where we have ideal gas behavior, but not necessarily ideal solution
and that
behavior.
is generally going to be quite good if we don't go into high pressure.
I'm wondering if number 2 is like the reverse of that. Is that where we have like
I think it's a little bit wrong to just say it's the reverse of that. It's different.
Okay.
But all of the non-ideality in this situation, I'm going to talk about it a bit more. Here is what the KIs look like, and if you take a look at them here, there are no hats over anything. These are all pure component properties that are involved here. So any non-ideality associated with the system itself then is associated with non-ideality of the pure components that make up the system. And that's, if you examine this, you see that that's what comes out. So the Ki that describes our vapor-liquid equilibrium depends only on P and T, independent of composition. And this works well, as I know here, for light hydrocarbon mixtures, which was so important in the earlier days of CHEME when half the chemies worked in the petroleum industry. Under these circumstances, we can express a huge amount of data that describes systems of this type using what we call a nomograph. Everybody know what a nomograph is? Anybody? Okay, well, I'm going to show you. But I'm going to go over here onto another PowerPoint if this machine lets me do it. Doesn't want to let me do it. Well, there is a nomograph. But this is what I wanted to show you, but I'm not seem to be able to do the animations because the action button doesn't show up. Unless anybody knows how to do this.
Is there a slideshow on the top bar?
Come up here and help me if you would. Because the configuration is different than when I'm working at my desk, for whatever reason. There's no action button.
Go from start, maybe? Is that right?
No,
You can press it.
I want to be able to go back and.
Here, when you press the pen, you're trying to draw. What's the animation?
Well, I should be able to show you if I can get it to work, huh? So there's no action button, so. Okay, I think we got it as good as we can. Thanks so much. So great to have somebody from the younger generation. So here's an nomograph for you. And let's expand a little bit to see what we've got here. We've got methane, if you can read 90 degrees here, methane, ethylene, ethane, propylene, blah, 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 a number of them here. And what I've got over on the left-hand side, I wish I could move over to get it a little more centered, I've got pressure in pounds per square inch, and here I've got temperature in degrees Fahrenheit. And then I've got a curve here, which apparently gives me data for each and every one of these components. So let's see if it lets me go to the next page. No, it doesn't seem to want to do that.
Can you zoom out fully, then swing?
There we go. Now I've blown up a little bit here so we can see a little bit more carefully. It seems to not want to be giving me everything on the left-hand side. Well, we got pressure over on the left-hand side, whether you can see it or not. So let's say I'm interested in calculating something at some given pressure over here. Well, there I got it, but not the way I wanted it. Oh, it's really screwed up. It's fairly unbelievable. Trying to force feed it here. But if I wanted to get the value of K at a particular pressure, and a particular temperature, I would just plot those on each side, then draw a straight line between them and look at the intersection with the line for the particular material, and that would give me the K factor for that. In this case, it came out to be for methane at the value that I wanted to show you as 64. But it's really acting up here on me. Well, this is so sad because this is quite a nice. Yeah, it's a little bit off. You can see it there. So let's look at an example here where we can solve using what I call the K-factor method. Once we've got K-factors for the components that make up our system, we can quite easily solve any of the kinds of problems we've been solving. That is to get bubble point pressures or temperatures, or dew point pressures and temperatures quite quickly by nomographic construction. So as an example to illustrate that, I'm saying let's find the dew point and the liquid composition for a vapor mixture, which is 30% methane, 50% ethylene, and 20% propylene at 0 degrees Fahrenheit. So we solve these problems in the usual way. The phase of unknown composition is the liquid, so I write down the expression that sums the mole fractions in that liquid phase to unity. There it is. Then I will write in the equilibrium equations for each of those, and now it's going to be in the form of K factors. And I know the y's, and so I can just plug those in, so here I go. So I need to find the set of K factors. In other words, I need to find the pressure that will give me K factors that satisfy this equation. So here are the three components. And I don't know what it is, so I'll just make a wild stab. I'll try maybe 200 psi. And that will give me K factors for the three components. There they are. Just read off the nomograph. But when I sum them up, I get something quite a bit less than 1. So that means the pressure wasn't high enough. So I'll just try a new pressure that's very easy to do. I'll jump to 200 psi, and that will bring me to these values of K that I get just reading it off for the three different components. And I almost hit it on the nose with that. So I can back off just a little, let's say to 195, and I've hit it on the nose and the problem is solved. So you can see for these types of problems, this is a quickie way to get answers if you have the nomograph. So that's what I mean by K-factor method, and that's going to be helpful to us in setting up other kinds of problems. So to sum up what we've got here, I've got the bubble point pressure that I want, it's 195 psi. And the mole fractions in the liquid phase are calculated here, just as indicated from the K factors that we evaluated.
Where did the K factors come from? The data, where did the data?
That had to come from measurements. So measurements led to those funny snaky looking curves.
And the measurements were taken from pure substances?
They're for pure substances, yeah.
And so we can still use them with mixtures and stuff?
In this case,
Yeah.
when they're so similar chemically to one another that we can assume validity of the
hydrocarbons. Okay.
Yeah. So that leaves us with a bit of time so I can get started on the next topic, also which is not in the book, but a very important topic. I think this is item, yeah, let's make a new page here. If it lets me. No, it doesn't want to let me. And these are what I call flash calculations. So it's a rather different kind of problem, but one of the first that you're going to see when you do separation processes in Chemical Engineering 435. So let me draw a picture of what I mean by these, and we probably won't be able to finish this today, but we can get started and then finish it next week. So let's imagine that I've got what I call here a flash drum. I have a feed going into it, and the assumption is that it will break itself up into a liquid and a vapor. So I have some feed going in, and then I have some vapor fraction, and I'm going to use that funny looking capital V, and I have a liquid fraction. Let's call that L, capital script L. And then of course I've got in this vapor, I've got the composition in the vapor, and here I've got, I can draw that. And the flash drum itself is at some given temperature and pressure. We usually will indicate the feed composition here with the letter Z. So the problem now is a little different than what we looked at so far. So given the feed composition, and that's this Zi, and the temperature and pressure of the flash drum, what we want to calculate is, we want to know how much of that splits. So let's say we want to calculate the vapor fraction and the compositions of both phases. So this is a typical flash calculation. And before we get started with that, let's recognize that this is different than anything that we've done so far. In that we now, in these kinds of problems, specify both the physical variables, pressure and the temperature. And we also have some given overall inventory, which we didn't specify before.